Welcome to our 7th lesson in the Engineering Design Process series. Today we're going to be talking about prototyping for motor selection. I'm Denny Davis. Again, I'm a retired engineering professor, and I'll be leading the discussion today. As we move through the design process, we're now at the stage of prototyping and testing in order to make detailed decisions for our design solution. We're going to talk today about using simulations or math modeling to help in this process of making these detailed decisions. What is a simulation? A simulation is simply imitating a process or performance. It may be the production of a computer model for purposes of studying behaviors, or it might be modeling dynamic interactions to gain understanding that we need to make these decisions. We're going to talk today about using simulations and math modeling for selecting motors and understanding their performance. We're going to look at an example where a motor is driving a static load. We'll look at a case where the load that the motor handles is varied. And finally, we'll look in more detail at a dynamic system where a motor is part of that, so we have a much more complex interaction. Let's begin by looking at motor characteristics. We're typically using DC motors, direct current motors, and their performance is often described by a set of motor curves such as shown here. These curves give the characteristics of the motor. They are usually a plot of torque or other variables as a function of motor speed. So we see that torque typically is maximum at stall condition when the shaft is not turning, but it decreases linearly as the motor speed increases. We notice that the current is also going to be maximum when the motor is stalled and decrease until it reaches free speed. Efficiency, however, peaks somewhere at the higher motor speeds when the torque is lower, and that's an important consideration in our selecting the right motor. So I've mentioned torque. What is torque? The torque is really effort to cause rotational motion or to oppose and resist rotational motion. So it's like a force, but it deals with rotation. It's defined as the product of a force and the lever arm that's used in causing this rotation. What is a lever arm? It's the perpendicular distance from the force to the axis of rotation. So in the case of the wheel that's shown, and the force pushing downward on the edge of the wheel, the lever arm here is designated by L, the distance perpendicular from the force to that point of rotation. The torque is then calculated as a product of the force and that lever arm, and it will have units perhaps of pound inches or newton meters. A couple of other examples we could look at. We take a look at the force F1. Notice that its distance from the rotation is designated by a lever arm L1. So its lever arm is shorter than the lever arm for the initial force we were looking at. And its torque about the center is equal to F1 times L1. If we look at F2, notice that it's acting right through the line that extends up to the axis of rotation. So its lever arm is 0, and therefore its torque, or its tendency to rotate that wheel, is 0. For more discussion of forces and torques, I encourage you to look at section 2A in the Pre-Engineering Primer, 2nd edition. So if we understand what the motor characteristics are, how do we use this to match the motor to a load? The operating point is the set of conditions at which the motor is operating when it's in equilibrium with the load. So shown in this diagram, we have a load indicated by the blue line. That load varies a bit with speed, rotational speed, but the point of intersection between this load torque curve and the output torque curve for the motor defines the operating point for this motor under this load condition. Notice that this operating point indicates what the speed and torque are. The vertical line through the operating point defines the speed. The horizontal line defines the motor torque. Notice also that the efficiency can be defined vertically on that line as well. But if you look at a condition where the load on the motor is 0, so it's freewheeling, as indicated by the red line on the right side. The speed of the motor is max, it's at its free speed. The efficiency is 0, and the output torque is 0. On the other hand, if we look at the cases where the maximum load is on the motor will stall, so its rotation is 0. Its torque is maximum, and you'll notice the current drawn by the motor is also maximum. Again, I refer you to the Pre-Engineering Primer 2nd edition, in this case section 7B on electric motors, for more discussion. Let's now apply motor performance to a case where we have a constant load applied to this motor. We have a motor here acting through a gearbox, turning a wheel, and we have a cord wrapped around this wheel, so that as the motor turns the shaft on the gearbox, the cord is gathered on this wheel to lift the weight. We have a certain torque acting in this situation. So what is the torque from the cord, that weight pulling on the cord? The torque, as you recall, is a product of R, in this case the lever arm, and the weight being applied. So the torque applied by the cord is R times W, 20 pounds times 1 inch, or 20 pound-inches. Because we have this gearbox, in this case a 1 to 5 gearbox, where the output shaft speed is 1/5 the motor speed, the output shaft torque is 5 times the motor torque. We can then determine the load at the motor. The torque load on the motor is going to be 1/5 of what was applied out there at the wheel by the cord. So 1/5 of 20 pound-inches is 4 pound-inches. Now, as we choose a motor, we have specifications that are usually published with that motor. Stalled torque in this case being 175 ounce-inches, free speed 340 RPM. Notice ounce-inches. So let's go back to the load torque. Convert that to ounce-inches as well by multiplying pound-inches by 16 ounces per pound. We get 64 ounce-inches. So now, think about these two numbers. The motor can put out a maximum torque of 175 ounce-inches. It's going to require 64 to lift this weight, so it means we do have adequate torque. So, if we have the 64 ounce-inches, let's look at our motor curve and see how this applies. With the 175 ounces ounce-inches of torque. In the free speed, we can draw a straight line which defines the motor torque as the speed of the motor changes. And think again about that 64 ounce-inches. From this information, we should be able to define other operating conditions. We put the 64 ounce-inches on the graph where that intersects with the motor torque defines the operating condition. So from this, we get 64 ounce-inches as the motor torque. The shaft speed we read directly from the graph, which is the speed at which that operating condition exists, 210 RPM. Then, knowing the characteristics of the gearbox, the gearbox speed would be 1/5 at 210 or 42 RPM. The lift speed is going to be based upon the RPM and the circumference of that wheel, which is 2 pi r. That gives us a total 264 inches per minute as the speed of the lift. That's the rate at which that weight would be lifted. Let's take a case now where the load is actually varying, so it's not a constant. We have a crane rotating around a pivot point on its lower end. It's lifting a weight W, and that crane will change in its angle. Theta will change as the load is being lifted or lowered. The torque then of this crane load can be calculated, but note that it's not going to be constant because the lever arm out to that load changes as the inclination of this crane changes. So we'll look at the torque as theta, that angle of inclination changes. We can calculate that as the lever arm is L times cosine of theta. Multiply that by the weight. That then gives us 48 cosine theta pound-inches. Now if we want that in ounce-inches, we multiply by 16, which gives us 768 times cosine of the angle in terms of ounce-inches. So that means we can complete this table and show what the ounce-inches, the load, the torque load, is as that angle changes. Now the torque on the motor is affected by the gear ratio. The torque at the motor is going to be 1/6 the torque applied by the crane. So 1/6 gives us 128 times the cosine of the angle theta. So then we can complete the table like this. So we can define what the torque acting at the motor is as the crane angle changes. We can look at the motor performance based upon the motor curve that we have and understanding some of the characteristics of the crane. As the crane angle changes, the operating point is going to correspond to the torque for each of those angles. And these triangular symbols indicate the operating point as the crane changes its angle. The motor rotation in terms of RPM is going to be read directly from the graph because the motor speed corresponds to the motor torque for each of those triangular symbols. I simply read those numbers. So the motor RPM varies between 90 and 290 for these different angles. The crane rotation is a function of the motor speed. It's 1/6 the RPM, so we can determine what the rotational speed of that crane is as it passes each of these angles. The crane end speed then is determined by the length of the crane, 2 pi L being the circumference of that circular arc that the end would pass through, multiplied by the RPM. Now, if we're talking about the actual speed of the load, it's the vertical component of the crane endpoint speed. So that's the crane endpoint speed multiplied by the cosine of the angle. So you see, we can determine many things about the performance once we match the torque and the motor conditions, and then do a few calculations based upon the geometry of our system. Note also that as we look at efficiency of the motor and see the different points at which the motor will be operating, we can determine the efficiency at each of those conditions. Let's now look at a more complex system where we have 2 motors driving 2 flywheels, and these flywheels are going to be launching a ball. We define the ball velocity that we want, an angle of launch, and then determine how we can best define details of our system to accomplish the scoring in this goal under the conditions that we're limited to. So as we begin analyzing, we always need to stop and think about what are the questions we're trying to answer. One of them is what launch velocity and angle are best to achieve the scoring that we're trying to do. Secondly, what motor and gear reduction are needed in order to get this launch velocity. Third, how much reduction in flywheel speed can we expect as the ball is launched? Fourth, how much time then is needed to get the flywheels back up to speed after the launch of one ball, so we could then introduce another one for a launch. And fifth, how does the maximum of inertia of the flywheel, that is the inertial characteristic of the flywheel, how does that affect the system's performance? As we begin to simulate the ball trajectory, we fall back on equations that are established for a projectile. The x, or horizontal position, is equal to its initial position plus the horizontal component of its launch velocity times the time since it was launched. The y component here is also defined by initial y position, the vertical component of velocity times time, plus 1/2 the acceleration in the vertical direction, which is our gravitational constant, times the square of time. So with this information, we can set up a spreadsheet for calculating different quantities of interest. We can define some initial velocities and initial angles for launch, and then for each of these conditions we can calculate, of course, the horizontal component of that launch velocity, the vertical component of the launch velocity. If we want to determine positions at incremental values of the horizontal, so that as we increase horizontally, what is the change in y? We can define that increment that we desire. From that, determine how much time it takes for the projectile to travel that far in x. And with that time interval, we can calculate using the equations above. We can then define what the x value is at that point in time, the y value, and for each different projectile velocity and angle, we can determine the vertical position. So we begin by defining the initial vertical position and horizontal position. In this case, because our launch is going to start not at the floor level, but at some height in the robot, let's say 0.2 meters, that becomes our Y initial. We then find the Y positions at each successive time interval or X interval, so we can determine what the path will be for each of these velocities and angles for the launch. These results then will produce for us trajectories that we can plot as shown here. Each different line indicates the trajectory for a given launch velocity and launch angle. So with this information available, we need to ask, what are we looking for from this? We can develop a table then to define those specific characteristics of interest. One question might be, how much time did it take to score? That is, how much time from launch to where it gets to the center of the goal. What was a maximum Y value? How high did it go? How far did it travel horizontally before it reached the center of the goal? And the last column here is how much vertical clearance did the ball have as it went over the near edge of the goal. So with this simulation, we can calculate each of these quantities and get information like this. And then we begin thinking what values are most desirable for the performance of our system. If we first look at distance between the launch point and the center of the goal, horizontal distance, in other words, how far away is the robot, you might see that if we're too far away or too close, there may be complications. So we might rule out those conditions that are enclosed in these boxes, too far or too close. We also might say, all right, if the ball is getting too high, it might be dangerously near the 2-meter height where we would get a penalty. So we want to stay away from conditions that produce this high launch. We also might notice that we don't want a real close clearance as it goes over the near edge of our goal. So rule out conditions that give us just a small clearance above the edge, because any variations in the trajectory could cause a miss. So that leaves us with one condition that appears to be best, 5.5 meters per second at a 75-degree launch angle. So this simulation has given us information to choose the best launch velocity and angle. So what about the motor then? What's the best motor and drive? We identified the speed of the launch, 5.5 meters per second. We're assuming that's the rim speed on the flywheel, which is equal to the radius of the flywheel times its angular velocity. So we can calculate then that the angular velocity for the flywheel needs to be 55 radians per second. Again, we look at the motor curve and see what that tells us. We'd like to be in a high efficiency condition, which means about 30 radians per second. The ratio then between the flywheel rotational speed and the motor speed is 1.8. Let's say we chose to have a gear ratio of 2 and not 1.8, which will then give us a motor rotational speed of 22.5 radians per second, and our performance indicated by that red line, getting us still relatively good efficiency, but operating at 22.5 radians per second and giving us the rim velocity speed that we need for launching the ball. As we move ahead to model the motor torque, let's look at the motor curves and note that, number one, we need to convert the torque that we get from the motor information into the units we're going to use for our calculations. Since I'm going to use SI units, I convert the torque to Newton meters and the speed to radians per second. And notice that the torque varies linearly with motor speed. That means that I can easily determine an equation that describes that performance. The torque is equal to 1.24, which is the stall torque, minus the motor speed divided by 35.6, which happens to be the free speed of the motor, multiplied by 1.24. So we can now represent in our math modeling the motor torque by this equation. So next, what happens to the flywheel speed during the launch and speed recovery? Let's think this through for a moment. We're going to begin at time 0 when we launch the ball. It's going to take a certain amount of time to complete that launch, up to T1. After that, we begin recovery where the flywheels again pick up speed to where they return to their initial launch speed. So during the launch, the flywheel will transfer its energy to the ball, as much energy as the ball needs for its launch velocity. The motor energy that's put out during this period of time is going to be transferred to the flywheel, and the flywheel is going to slow depending upon the difference between how much energy the ball takes and how much energy the motor adds to it. Then during the recovery period, the motor energy is transferred to the flywheel, and the flywheel recovers its original speed. Now we're assuming that we're going to continue adding power until the flywheel returns to the desired speed for the launch. And then, if we're going to launch a second ball, we just repeat the same line of reasoning, because we're starting again from the same conditions where we started for the first launch. Well, we can then model these responses. We have to assume a certain mass for the ball, velocity for the ball we've defined, mass moment of inertia I for the flywheel, and this I was calculated based on the assumption that our mass of the flywheel was 0.1 kilogram, its radius was 0.1 meter, and we're assuming that it's like a cylinder spinning about its axis to give us that mass moment of inertia around that central axis. From this, we can answer some different questions. Our simulation will give us information to answer these questions. First, what's the initial flywheel rim speed? Well, we calculated that already. That's 5.5 meters per second. With this speed and the ball passing through there, how long is a ball in the launch? So what's the launch duration? It comes out to be somewhere on the order of 1/100th of a second. And how much energy is transferred to the ball in the launch? Well, it's the amount of energy that the ball needs, or the kinetic energy of the ball, when it's initially launched. So that's calculated. During that same increment of time, the motor is putting energy into the flywheel based on the torque that it's applying, the amount of time, and so on. And so we can determine how much energy the motor added to the flywheel. Notice that 0.76, 0.14, that the motor is adding less than the flywheel is transferring to the ball. So then, what's the flywheel rim speed after launch. Based on this energy loss, we can calculate a new speed of the flywheel and then its rim velocity, 3.9 meters per second. Now, notice that it started at 5.5 and it dropped to 3.9. And how much time would it take to recover, get back up to the wheel speed desired? We can calculate this based on angular acceleration, the torque applied, and how much time it takes to increase the speed from the speed immediately after launch up to the speed that we wanted initially. So with this information, we can vary different properties. For example, we can vary the moment of inertia of the flywheel and see how that affects things. Here's a graph showing the initial velocity, the speed reduction that occurs after launch, which is the orange line. Excuse me, it's the gray line. But if we have the motor adding some energy at the same time, it actually counters some of that loss. And so with the motor adding energy at the same time as a launch, the drop in flywheel rim velocity is significantly less. Notice as we go left to right, the dashed line is the initial assumption of the mass moment of inertia for the flywheel. But as we increase that mass moment of inertia, and moving to the right, we see that the drop in velocity becomes less and less. So it tells us that the flywheel mass moment of inertia does affect how much velocity change occurs in the flywheel. And it would also affect how long it took to recover. So we see that the larger flywheel mass moment inertia reduces the velocity drop. The motor input in the launch reduces that drop. We also see, if we look closely at the amount of time to recover speed, that the difference in recovery time is very little, even as this mass moment of inertia changes. The speed may drop more when mass moment of inertia is small, but it also then provides less resistance for speeding up the flywheels after the launch, so it recovers more quickly than we would expect. So it essentially has a small effect. The mass moment inertia has a very small effect on the amount of time required to get the flywheels back up to launch speed. So let's look now in a summary of what we've accomplished. We were attempting to define details of our design. We used simulation techniques to do calculations and figure out these details. For the flywheel, we found that 0.10 meter was probably about the right size because much larger and it won't fit in the robot and allow the ball to fit between two flywheels. We found from our simulations that the launch angle of 75 degrees, velocity of 5.5 meters per second gave us the range and height that we wanted and met some of the other conditions that were important for a good competitive robot in scoring in this particular goal. We found that the mass moment of inertia, greater value mass moment of inertia gives a more constant launch velocity. It's going to slow down less with this larger mass moment of inertia, so we're likely to have a more consistent launch velocity of the ball. In terms of the motor, we found that the Neverest 20, assuming we had one per flywheel, does give adequate torque and speed. And we found that with the ratio of 2 to 1 in between motor rotational speed and flywheel rotational speed worked relatively well for our system. So we were able to define a number of things through the use of some of these simulations. Now, let's pick up some points here. We learned from the simulations that torque or speed will help us pick the best motor. In this last simulation we did, we had to have certain speed to get the ball launch velocity and the torque to get the recovery. And so the combination of torque and speed will help us figure out what's best. We have to be sure that in our simulations that we have our motor curves in the same units as we're going to use in our modeling. We want to define the motor curve in terms of an equation so that can easily fit into a spreadsheet. And then when we're modeling the system itself, we want to ask what are the important questions. Make sure that in our calculations we give the information we need. We develop a model then to give results that fit the questions. We identify parameters we want to vary in order to see how these parameters affect performance. We generate results for the varied parameters of interest. Based on all this information, we then choose the best parameters based on our practical considerations. So we chose the launch angle and velocity. We chose the motor and the ratio, the speeds between motor and flywheel based on some practical considerations. So, to this point, we've gone through a number of steps in our design process. We have been math modeling, simulating in order to get some of the details pinned down for our solution. And we'll continue one more lesson where we do some simulations, but this next time to look at how we can control dynamic conditions in our robot so that we don't get oscillations but get stable operating conditions. So join us again next time. Again, thank you for joining us. We look forward to seeing you again next time. And thank you again to FIRST for inspiring this kind of activity, that is, sporting events for the mind. See you next time.